that we are now talking about the Earth's history. And what we're going to focus on for today and tomorrow are the early years, the years when you don't want to take your time machine, the years when the Earth is forming and cooling and setting itself up basically for the kind of life we know. So that would be Hadean, Archean, and Proterozoic eras. Let's talk about those. Remember our sense of scale and how most of time has been Precambrian time with simple one-celled organisms, and that we have eras to memorize. We haven't gotten to periods yet, but 6 eras so far, and general trends in each one. And then we use dichotomous keys on sharks, and here we are. So I'm going to show you a video that deals with some of the stuff about the way Earth formed, but let's talk about it first. And if you're wondering how we could possibly know how the Earth formed since nobody was there to see it, obviously, the answer is simply that we know how planets like Earth form. Like, there's no reason the Earth should be different than other planets that form around stars like the Sun, of which there are many. Basically, what happens is when a star forms, stuff starts to gather around it because it has mass. It attracts rings of, let's call it, cosmic debris and dust and chunks of minerals. And those gatherings eventually become clusters because, of course, gravity isn't just what sticks you to the planet or what makes my pen drop when I drop it. It's what all things with mass attract each other with. Right? Everything with mass attracts everything else with mass. And so when stuff in empty space gets near other stuff, a lot of times they'll stick together because of gravity, right? Stuff attracts other stuff. But a cluster of cosmic debris is not a planet. What has to happen for that to happen, a layered structure like the Earth, for those layers to form, what has to happen? You know? It has to get really hot because it has to melt. Because only by melting are the dense things going to sink to the middle, and the medium density things going to form the surface, and the light things going to form the atmosphere. And what had to happen for it to melt was for stuff to smack into it with enough energy to create enough heat to melt it. One of those things was big enough that we call it Mars-sized. That's actually the one that tore loose the piece that became the moon. But regardless, those space impacts create enough heat to melt the cluster of cosmic junk. And that's when we get this like stratification, this layering of the Earth. The ore forms from nickel and iron, dense stuff that goes down the middle. The crust and the mantle form from the medium density stuff floating on top of the core. And then the really light stuff, mostly nitrogen, forms the atmosphere. Well, nitrogen and water. A couple things about that atmosphere. You know, even if you find a way to deal with the heat, and you go back in your time machine to the early Earth, the atmosphere is also not breathable. In fact, completely toxic. Hydrogen cyanide is there in a high enough concentration to totally kill you. Carbon dioxide and carbon monoxide, both there in pretty high concentrations. Hydrogen sulfide, not pleasant. One breath, and it would kill you. if it's any consolation, like maybe if you keeled over, face up, right before you died, you'd notice the sky was a lovely shade of pinkish orange, because that's what color those chemicals would have been to light. But we're still Hadean here, right? We're still in the fry your face kind of time period. It's not till 4 billion years ago that the Earth cools enough even for there to be rocks, right? Everything's pretty much molten before that. Still, even with rocks, there's volcanic activity more often than not. By 3.8, so another couple 100 million years later, that's the point at which water can be liquid, right? The point at which the temperature on Earth has dropped below the boiling point, which is 212 degrees Fahrenheit. And that's when the oceans form. And we're entering, or have already entered really, the Archean era. Questions so far? How did it get there? Same way the other stuff got there, right? It was a cluster of stuff. I guess the water would have been ice at first. And then when the heat came, it would have been, vapor. And by the time it cools enough, then the vapor becomes water and falls to the surface. Yep.
I know you said that we know all this because we watch other planets do, but how do we know like it happened 4 billion years ago? That's like a large amount of time scale.
It is. It's a huge time scale. And that's not my area of expertise, but basically radioactive dating and sort of knowledge of the time scale other planets have operated on, that's our best guess. We can date living things back to 3.7 billion years at this point. And that I think that 4.6 I told you used to be slightly less. They adjust stuff as current understanding comes along. But I don't have a great answer for that. Okay, so I can talk about this, but let's hear from somebody else with some visual aids. This is just 5 minutes or so, but it's pretty good. Gives you a little more of a visual sense of what's going on. So from there, we got to get to life, which is hard because, first of all those complicated chemicals you learned about and built at the beginning of the year, they aren't there yet. We don't even have the stuff life is made of yet. And so that's a question scientists have wrestled with for quite a while now, starting with some scientists in the 50s, as early as the 50s, setting up a gizmo like this. Their names were Miller and Urey. And what they basically wanted to do was figure out if the kind of organic molecules life is made of can be spontaneously formed in an environment like the early Earth. So they tried to set up an experiment that simulated the early Earth. So this is in the 1950s. They're basically taking a bunch of glassware and rigging it up together. And simulating, by which I mean putting the chemicals that their understanding of the early Earth said were there, enclosed in glassware. And so they set up a gizmo like this, and there's water there that they can take samples from easily. And they leave it overnight. Come back in the morning, nothing new in there. And then they get the idea, well, hey, there would have been storms, right? There'd be electrical activity on the early Earth, lightning, right? So let's pass some electricity through this simulation of the early atmosphere. And by doing that, the next time they check those fluids, they find several of the amino acids that proteins are made of. Doesn't sound like much to a normal person, but you know how powerful proteins are. They're kind of the main job-doing parts of the cell. Fast forward 40 years or so, and another group of scientists decides to kind of redo Miller and Urey's stuff because understanding has changed a bit. The theories have been adjusted as far as just which chemicals in what concentrations there were. And so they do a more accurate simulation of the early Earth's atmosphere with some of the chemicals we didn't know about in the 50s. And in this case, they actually get, in addition to the amino acids, they get cytosine and uracil, which you know as components of nucleic acids, right? They're nitrogenous bases. So pretty cool set of experiments showing that, yeah, some of these things that living cells are built from would have been able to form on an early planet like Earth. Put those chemicals together and add some heat and some electricity, and you start getting randomly, spontaneously, some of the things that cells are made from. However, it's not cells, right? You can make chemicals all day long, but we're talking about life. And so here's where the big question comes. Big one that kind of makes a lot of folks clench up a little. Think up. It's just going to be something I don't want to hear. That's fair. What's cool is I get to say my favorite thing, which is, we don't know. I love mysteries. And this is one. Nobody's been able to do it. No one's ever created the conditions of the early Earth and seen living cells spontaneously form. So we don't know. I can tell you two things that have been done that maybe give us some clues. And the rest is up to you. Number one, if you put the right organic molecules, lipids and nucleic acids mainly, sorry, lipids and proteins mainly, amino acids is what I meant, you can get these things called microspheres. The lipids will do that thing we showed in water. You know, they'll put their little tails together and form membrane-like structures. Not quite as complicated as cell membranes, but membrane-like double layers of lipids. The proteins even do some basic things inside sometimes, like simple storage and release of energy, which is pretty cool. These microspheres will let certain things in and out, but not others, like real cell membranes do. We call them proteinaceous microspheres, which is a mouthful. They're not cells. Proteinaceous microspheres are not cells, not alive, but maybe this was like the first baby step, right? Maybe from microspheres eventually come real cells. But again, it hasn't been done. And the other thing I can tell you is that based on what we know about DNA and RNA, because that's the next step. Proteinaceous microspheres basically don't have reproductive capability, right? They don't have genetic material. And so that's the next problem to tackle. And the problem is that DNA would be kind of a lousy first genetic material. DNA isn't very good at doing anything but replicating itself and being read by other molecules. And so the general consensus among scientists is that RNA, if you're going to pick a genetic material to start with, if cells form spontaneously, the genetic material you would want them to have would be RNA. It would be a much better all-purpose molecule. Because not only can it store information and copy itself, but it can also go do jobs. It can form the shapes like proteins do and go make stuff happen, go catalyze reactions like enzymes do. You hear that? What was that? Okay, that's weird. So yeah, the general consensus is, and this is called the RNA world hypothesis, is that the first life was probably RNA based, just based on its suitability to be an all-purpose genetic molecule over DNA, and that DNA would have come later as sort of an evolutionary adaptation dividing labor. But that's about it. I'm not going to say anything else about how life formed because we don't know a lot. We know it did. It wasn't there, and then it was. Celine.
Why didn't the moon evolve like Earth?
You mean why didn't life form on the moon? Lack of atmosphere, most likely, and water, lack of water. Everywhere we see life, water tends to be involved. That's kind of what we look for. So probably that.
How do the toxic gases like cyanide make it filter out of our atmosphere?
Ooh, good question. I don't know where the cyanide went. See if you can find out. Other questions? I think that's as far as I'm going to take you today. What did I give you yesterday? Sharks? How about we go long term? How about we go, did the Novolab stuff go okay? Did some of you work ahead a little bit? Couple? Okay. Well, let's just say the whole thing, all 6 missions need to be done tomorrow. Kidding. How long you want? You want the weekend? How about Monday? All 6 done for Monday. And the only other packet I want to give you is for mission 5. So missions 1 and 5 have packets. All 6 need to be done in your account so that you can mouse over your little character and show me, hey, here it shows that I did all 6 missions, and then you've got the 2 packets. Okay. So long-term assignment is Monday. So we're close. We're close to being done with all the state technical material. Expect practice, state testing coming your way soon. Nothing too scary, just to give you a look at it. I've already been cherry picking a couple of state test questions and sticking it into your you take it. Yeah, I get it. Sorry. Not that I don't like it.